structural engineer is always a part of the design team for every residential project I do. And as the Outpost project plans and elevations are taking shape, it's time to begin thinking about how we design the structure, foundation, framing, and finding a good engineer really does expand what's possible. And importantly, it can begin shaping the design.
We ought to be thinking about what's the relationship between the box, the building, that wants to move like this when the wind blows on it. The ledge below is what we need to attach it to. Mm-hmm. And so how do we resolve the wind against the broadside of the barn? Laterally down to the ledge. Do we pour chunks of concrete that aren't going to move in certain areas? Although you might see those, is that a cost-effective way to get the job done as compared to 8 or 10 sets of stainless steel cross bracing, for example? Mm-hmm. They look different, they do the same job. Pouring concrete on an island, especially a remote island, is a big deal. There are quality control considerations. Mm-hmm. So we can't have this, we can't use the same palette of materials on an island, let alone a remote island, that we can on the mainland. Right. So the quality of concrete may be lower if it's site mixed, if it may be inconsistent. While you can develop those strengths in the lab easy enough, we at times are concerned about the quality of that concrete, and if that's what's holding the building up, then you want to try to avoid that. We probably want to use a series of timber posts that have some typical, probably stainless, connection to the ledge. Okay. I've done enough work on this island to know that it's not a smooth, consistent ledge. It's fairly irregular. Yes. And so it may be that if you want to architecturally see the pecking order of building, post, maybe stainless connection to ledge might be 3 feet away. Yeah. If ledge was clean, consistent, and exposed 6 inches below grade, it would be possible to install a stainless steel post base, grouted level, pin to ledge. And it may be a custom bent plate. It's actually cheaper than an off-the-shelf stainless post base typically. So because ledge elevations are fairly inconsistent, I'm guessing that we probably aren't going to get away from pouring some amount of concrete pin to ledge. And that basically will set us up to provide some predictable top of pier elevations that will be helpful during the design process and also during our shop drawing review of any steel components. It's good to understand as we're tracking loads down through the building what we're going to have for a dance floor on which to land that. So it's good to talk about the site, ledge, post versus concrete, material palette at first, and then we actually go up to the top of the building and talk about which areas are vaulted, generally what the thickness of roof cavities will be. Is it a 2x12, 10, 8, etc.? And there may be varying. It may be that low roofs are thinner because of fascias, etc. For sure. So now that we've talked about site conditions, it would be good to talk about your ideas relative to typical wall construction. Is it a 2x6 or 8 or 4 in areas? And then what are those roof planes? What are those roof cavity thicknesses? And based on your architectural, maybe insulation requirements, for example, the thickness of that roof cavity. It may be that I only need a 2x8 in a certain area, but you say, well, based on our anticipated insulation detail, we need at least a 2x10, and that may set up a typical soffit and fascia detail around the perimeter of the building.
Well, so this framing, 2x6, I think part of the idea here is that almost anybody could build this. So I think we have to keep it simple. In terms of relationships of roof surfaces, what I've tried to do on the elevations is really establish the profile of the building as being quite low. So I don't, we didn't discuss this, but this is a 12-foot wide volume here. This is 16 feet wide. So the intent is to keep everything scaled down and small, and really so that you are very close and connected to this environment. And so when you start folding that back into the elevations, the heights of these things are pretty small. So we're talking like a 7-foot ceiling in here in this entrance. And then, probably a 2x10 for the roof framing in here. And then I'm planning to frame a flat deck and then use tapered insulation on top of that to get to our scupper at one edge.
From a framing standpoint, we call that flat framing, right? When the framing and the sheathing over the top of it is flat, and then you add tapered rigid above that. Structurally, that's the easiest way to do it because you have a consistent wall plate elevation. Right. What's your sense? Are we talking green roof, ballast, etc., or if you were to climb up there, would you see the exposed black EPDM roof? It's very common. Sometimes you install a finish with some type over it.
Yeah. Ideally, we would install something, and we had talked about, hey, it'd be great if it was a stargazing deck, but once you do that, it sort of starts to level everything up. Yeah, so EPDM exposed is what I'm thinking.
Structurally, we like that because we don't have to carry the dead load of 3 or 4 inches of river stone or a green roof, for example, which have their own maintenance issues.
Right.
Yeah, so that's good. So given that span, I think that a 2x10 is going to work.
Okay. In the sort of pitched roof assemblies, I was thinking a 2x12.
A 16-ish foot span. We're in the ballpark for a 2x12, and if it's a 512, then generally speaking, we probably have a double top plate. We have a 2x12 rafter and a 2x6 stud. And then we can talk about the eave, whether or not there is an exposed tail. That's a little bit more difficult if that rafter was exposed, and whether or not that is actually the extent of the rafter, whether this is actually ladder framed, added to it. So
that's what I'm picturing. I'm picturing that I wanted a really minimal overhang, but we're pretty exposed here. So, just having a drip or something very close to this shingled wall surface, probably not the ideal thing. So if we do anything, it will be an added piece in here. And I'm still working as to, like ideally for me, that this surface would be very thin, and then we would bring, this is a metal roof, so the metal roof would sort of come like that, and this would just be almost like a drip edge. But if that's 6 inches, this needs to have some heft to it.
Sure. Depending on what this is, if there is an insulation plane, if it's not the case, but if we had an exposed deck here and we had an exposed rafter, sometimes we'll embed this thing up in that insulation plane. Fortunately, that's not the case here, and so whatever that is, we'll probably just add it to the side of the rafter. We refer to it really as an outrigger, but it's maybe a 2x4, for example, or if you want it to be even thinner, we'll just take a look at what is that cantilever out beyond the outside face of that stud.
I'm going to say it's 6 inches for now.
Oh, it's nothing, yeah. If it's only 6, it may even be applied. Because in such a case, we'd want the roof sheathing to be continuous, because that would be our tension tie. And if you have a continuous sheet there and you've got a ladder frame, thin soffit assembly there, then it could simply be applied and we wouldn't necessarily need to break that. It's handy to sheathe the building first and then apply that, but that's a detail for another day for us. If you simply were to cantilever the sheathing out there and then apply a finish to the underside of it, 6 inches is not much. But at the end of the day, you actually need a fascia to be straight. And when you have 2 sheets of roof sheathing, even though they're only cantilevering 6 inches, you need to double up a fascia of something, of some depth there, simply to allow your sheathing to sheathing sheets to not read. One thing that we need to consider is when we're choosing our palette of materials for this building in a remote environment, perhaps assembled by a small crew, whatever we use to build, it's going to get wet. And in an ideal world, and we do this at times, we actually prefab sections of buildings and they actually deliver it in pieces. And so the floor is framed within a few days, the walls are erected within a few days, the roof is on within a few days, and it's watertight-ish. It's probably not going to happen in this case. And so the more pieces of dimensional lumber we can use, for example, I was thinking down to the floor, and I'm jumping ahead, but it would be great to use dimensional lumber as compared to an engineered I-joist that doesn't perform as well when it sees some construction weather. So thinking about this detail, we just want to use parts and pieces that have some durability to them, even if they're small.
Quite often here on the coast, the structural design is heavily influenced by the lateral loads on a site. For example, on this site, which is really exposed, the winds exert horizontal forces that we need to trace all the way back into the foundation. And because we're using piers for our design, this starts to suggest a certain palette of materials and the types of connections we're going to use.
As we're thinking about connecting this building down to the ledge, that's main force, let's say, and I'm just guessing, 20 pounds a square foot applied to that vertical face. It's 14 feet tall. Well, that's 280 PLF, basically, for every length of wall in this direction, which is that right there. We've got 280, and so 24 feet. So bring out this beauty. 6,720 pounds of lateral load that we need to move down to the ledge. And so then we say, okay, this is a short course in lateral design here, but we have.
But that's, I mean, this is how you go ahead and do this.
This is what we'll do in our office, right?
For every component here.
Exactly. And so in this schematic kickoff meeting, we talk generally about the systems, and then we start to measure these components, figure out what the geometry of the building is, what the resulting loads are based on the site-specific snow, wind, etc. And then we figure out, okay, how much force do we actually have in these braces? Is this wood PT 4x8 brace actually going to work, which is where we're headed here in a minute, right? Because we said that the weak link of these systems is often the connections. So let's say that we have 6,720 pounds that needs to find its way down to the ledge. That's the load that ends up in the first floor deck, right, as it's moving in this direction. So the first floor deck is sheathed here, right? And so if this was a really long and skinny building here, it may be that you can't, to resist that 6720 in this direction, it may be that you actually need bracing at fairly regular intervals and not just at the two ends, because the wood diaphragm just can't bend that far. It's a beam. Sure. It has a width of 3/4 of an inch, and it has a depth of 12 feet. That's what a diaphragm is, right? It's a beam that spans, but this guy's only spanning 24 feet. So thinking ahead, it's likely that if we don't even consider any contribution from this block right here, we would only need bracing here, and we need, and we'll have half of that 67, a little bit over 3,000 pounds in each gable end, if you will. So then the question becomes 6720 divided by 2, we're at 3,400 pounds or so. Sheathing's going to be nailed to the beam. The load's easily going to be in this beam. If we have a wood frame floor and a PT 6x6 post and a PT 6x6 post, could it be as simple as not respecting any sort of architectural finish on these posts? But let's just think about structure here for a second. Could we simply take a PT 2x10 and nail it to this face and nail another to that face? So if we look at that condition, we're going to have a PT 6x6 post with maybe a stainless steel bent plate, and we're going to through bolt. That's going to be installed on a concrete pier that's pinned to ledge, and then we have a floor system up here, but what we're really interested in looking at is that connection right there. We really want to get this brace as close to the concrete pier where that's headed, so we don't induce any additional bending forces in that post.
Because that wants to sort of do that, right?
That's right, yeah. And we're thinking about 3,400 pounds here. So let's say you said architecturally that I just want a 2x8 there, because a 2x10 is a pretty significant thing to look at. So, okay, we might have a 2x8 there. And we have a PT 6x6 post that is 5.5 inches. And we have 3,400 pounds in this. Or maybe there are two of them. So let's say it's 1,700 pounds, one on each face of the post, for example. If you take a look at the wood design guide, it tells us what the minimum edge distances are from the edge of this brace to the center line of that bolt. And all of a sudden, 7.25 by 5.5, as we lay this out, is a tiny little space. And if you look at the capacity of this 1.5 wide member in the other direction, let's say you've got
one on each side.
Yeah, say we're looking in that direction.
Yep.
Let's say you've got one on each side. A 16 penny nail is good for 120 pounds, something like that.
Okay.
So 17 nails, could we fit that in here? Probably not. And even if you could, they'd rust and be gone in a few years. So a nailed connection there isn't going to work. I think we're going to have a difficult time making a bolted connection work as far as the capacity of that side member. This is called the side, this is called the main member. And so if you look in the wood design guide, you'll probably see that 5/8 diameter stainless steel bolt with an 1.5 inch side member is probably going to be good for 400, 500 pounds at most. And so 500, 1,000, you're going to be pretty close. Point being, we're either going to need a lot of wood braces or a handful of well-designed and repeatable stainless cross bracing. And so if this thing was a stainless brace, it's likely that we could have a through bolt and then make a connection between a stainless brace and an eye here, for example, and start to develop some of those.
Yeah, okay.
The key is to make the connection to the wood post, or if we can standardize these guys, it may be that we have a connection and it takes it right to the concrete through that off-the-shelf post base.
I'm just worried that we're not going to be able to find any kind of consistency. As I look at the site plan, it's all over the place. And so, and especially even given how things change from front to back on that unit, I don't want a big concrete piece that we're going to have to look at, that because I'm not sure I trust the level of finish that's going to happen with some of those concrete pieces. So to me, it's preferable here. Does this connection get a clevis? Like, does it come to that kind of a thing, or a pin, or how does that?
Yeah, it likely would be a through bolt or a bracket of some type that has perhaps an eye and then a clevis.
Okay.
So
the clevis is like.
That's right.
Here's our eye.
That's right. Yeah.
Right, and this gets tagged into the post, and you said that's a through bolt connection kind of.
Yeah, it's likely a through bolt depending on the angles. It may be that's a bracket of some type that's bolted, that's jacketed around the post, for example. Yeah. I think in an ideal world it would be a bolt, for example, an eye bolt, if the forces are low enough and we can actually develop that connection.
Okay. I'm fine with that as a look.
As we continued our discussion, we reviewed the first floor framing package and the exterior deck construction details, and finally the barn. And I wanted Al to address one of the most common objections I hear in the field during construction.
Is all this necessary? People have built buildings out on this island for, a couple hundred years, right?
You're absolutely right.
Like, this is a question I get all the time from builders saying, I can do the back of napkin calculation. That's a 2x10 for that floor, and it's 2x6 wall. I'll throw a few nails in it and call it good. Why do we go through all this trouble with these homes, with architecture in general?
Sure. Well, I think it comes down. There are a few variables. One is how aggressive is, or based on the architectural requirements of the building, how hard is the structure working? Yeah. And so if you look at this simple little box right here, the structure's not working very hard. I think it's going to work a little harder over here. A general contractor could easily assemble these details, and it would, for this little box, and it would perform quite well. As a consultant, I work for you, the architect, and it's your responsibility. I'm not trying to tell you how to do your job, but generally speaking, you are having a variety of conversations with the owner. And those are pretty deep conversations, and you are understanding their performance expectations for the building. It may be that the owners say, we want to use fairly inexpensive windows, for example. We're going to use wood finishes. We just want a clubhouse, and we don't want water to come through the roof. That's a far cry from a $100,000 lift slide door where the allowable deflection below that sill is 0. And so
that's where those things come into play, right? When we start doing
well before that.
Big openings.
That's right. But that's the white and yellow line.
Yeah.
For us as structural engineers. So that sort of describes the spectrum in which we work. And so my dad was a builder growing up, and I saw him build all sorts of things that structurally don't quote unquote work on paper, but they actually worked for him and his clients because they met the performance expectations that they had for the building. And so I think that there's a basic level of performance that if I put myself in a homeowner's shoes, I'm investing enough and I care enough about the product that I'm going to hire an architect. And I actually care that light switch is however many inches off the floor that you put it when you walk through the door. I don't know what it is, but you do, right?
Yes.
And so when they walk into that building, they may not know that, they may not always be directly aware of the benefits associated with hiring a professional, but they know that when they go into the bathroom that it works well because they were able to reach around the corner and turn the light on, right? When we don't do our jobs, yes, of course, a building could fall down, which doesn't happen except on a very rare occasion,
right,
on a different scale. But it's more that there's a crack in the sheetrock, or the plaster, or a window leaks, and people think that it could be a product failure, and it may be. But it's probably a combination of things. Yeah. It may be that window wasn't properly flashed. It may be that the building actually is moving just a little bit too much. And so if you look at the average 24, 36 home in a subdivision, the performance expectations are probably low. They've been built a million times. It's a commodity. People know how those go together. And so do you need a structural engineer to design those? No, you don't at all, or in a very rare case. But once there's something unique about the design, I think that's when professionals get rolled in to make sure that it performs as well as we as the professionals think it should, if that makes sense, based on our conversations with the owner. And that ultimately the owners are happy. And if you've got a building, if you've got windows that leak, for example, that's not performing particularly well.
Yeah, and I think there's also, I mean, we haven't talked about it much here, but there is also, architecture interfaces with structure, and I think the best architecture it exposes that structure for how it performs. It turns it into something beautiful, and I think that, that collaboration for me is if I have an aesthetic goal. And you're able to help me get there. It's an interesting conversation to talk about, well, if the goal is to pull the columns in here, there's lots of different ways of doing that. Here's the implications. For me, that's an interesting dialogue to have. And then, this doesn't have a lot of exposed structure in it, but for example, if I was gonna do that in here, this is the space I'd wanna do it. Putting those items on the table so that we can discuss them and really hash out not only what the structural implications are, but also from a cost standpoint. I mean, because all of these things are interrelated. That's the thing about architectural design is it's not just one thing. We have the builder that we're interfacing with, we have the structural goals, we have the architectural goals, function, aesthetics, all of these things kind of come together in this space. And I think that's, you sort of answered the question exactly how I hoped you would, in that, do we need an engineer to make sure that this thing doesn't fall down? Maybe not. But does it make it a better product? Does it make it architecture involving one? I think it does. To have you as an expert that contributes to the process in a meaningful way that actually shapes the design, that's where it's really important to me. I think
there's something interesting about as a consultant. So generally speaking, we're 10-ish% of an architect's fee if you actually look at the business plan, which means we actually need to cycle through 10 times the number of jobs that you do if we were to make it the equivalent living, which we do. And so we on some projects lightly touch. We may size a couple of beams. We may provide a full set of contract documents and construction administration services for other jobs. But we're the guys who are helping to put together the drawings that describe the bones of the building and how it connects to the ground, obviously. But we're also involved in 10 times the number of jobs, and we see stuff that doesn't work. And so if we occasionally offer architecture quietly out of the side of our mouth, offer architectural advice, it's because we're exposed to so many projects. And so it's not just the calculations to make sure the beam doesn't deflect. It's sort of a global view about the construction industry practices, what works and what doesn't work. And oftentimes is what doesn't work. And so I don't see anything here that doesn't work, but that's often our value too.
Yeah.
Now, these early meetings don't suggest the final solution, but knowing the structural forces that govern a project allow us to account for them and resolve them in a meaningful and hopefully elegant way. Oh, look at that baby. That is, what year is that? It might be the same one I have, the 9th edition.
Yes.
Let me see, I might have the 9th edition too. Look at that, the difference between an architect and an engineer. Who's doing more work here?
Yeah, right. Well, hopefully I'm using this and you're not.